All right, start out with any questions? I believe you have a test coming up in 2 days. Take that as no questions.
Oh, I do have a question.
Oh.
I was getting to where I was studying the 252 old tests. Do
The-
I need to study those? Because there were some symbols on there and I was like,
The 252 old tests are primarily there for the last problem. I think I had more worked out solutions for the circuit analysis than any of the other ones. There were, some of the problems on there are completely inappropriate for this class.
yeah, I was like, I don't think I remember learning some of the way these go. So that's the reason I was asking.
If you saw something like that or something like that, that's
I saw the top one.
it's the reverse of one of these. I'm sure that helps. Oh,
Yeah.
no, it all makes sense. It's called an integral.
Okay.
You get this near the end of Calc 1 or in Calc 2.
Oh, yeah, I haven't finished Calc 1 yet, so.
I only had Calc 1, so like, I felt like I should know it better, but that makes me feel better about the fact that I don't.
Yeah, I noticed that the 252 tests were pretty much repetitive, like in a lot of questions, so I was like, well, I'll just ask, just in case.
All right. Other questions? We seem to be missing people. But Janice is here. Enough of that. Can't start until John gets here. Maybe he's still in the old time.
My cats were like, where are you going? It's dark outside.
Oh, yeah. Yeah, that one really killed me.
So, fully moved in my face.
All right, we, I think last left off talking about sort of that cycle and the idea that if you have an electric field that's oscillating, that it will create a magnetic field, which creates an electric field, which creates a magnetic field, and so on, and thus the creation of an electromagnetic wave. So I'm going to go through, and it is going to be one of the most exciting classes. We're going to derive the speed of an electromagnetic wave. Yes. Some students, just to give you a heads up, some students just get really excited by it, and some students just practice their blank stare. Hopefully you'll be in the excitement category. However, there is some background. So if I have a position versus time graph, this is a cosine curve. Speed x of t equals cosine of t. That would be 2 pi. What does the velocity graph look like? What is the relationship between a velocity graph and a position graph?
Is it the slope?
Say it again?
Is it the slope?
It is indeed the slope. All right, so when you're finding the slope of a curve, you're looking actually at the slope of the tangent line. So what is the slope of a line that is horizontal?
0.
And so it's 0 here, it's 0 here, and it's 0 here. What can you tell me about the slope from here to here?
Negative.
All right, and so I know it's 0 here and here, so basically it's going to look something like that. And then from here to here. And what is this graph? Close? Yes. So my velocity is negative sine of t. And if we went down to the next one, acceleration. Well, let's figure out where it's 0 again. Just sort of say there when I pass the point where the slope is 0. There was some excitement in that. Feel it. All right. In this first region here, slope positive or negative. Notice it starts out as a steep slope and becomes less negative. And then in the next region,
Positive.
and the last region, what is this graph? And so we get the cycle here. If I start with cosine, I can start with sine also, but if I start with cosine, I get negative sine, then the slope of that is negative cosine, the slope of that is negative sine, again, positive sine, and then cosine, basically it cycles through. So if this is position, this is velocity, acceleration, jerk, snap, crackle, pop. It's flat. Or if this is position, then we get velocity, acceleration, jerk, snap, crackle, pop, and so on. It just will cycle through. Now let's amend it. Now I have x is equal, I'm dropping the vector symbols just for simplicity. X is equal to the cosine of 2t. What does that do to my graph here?
The variance was long.
Or the other direction? Yes? Everybody heard that? You want to say it again, like you mean it?
Half as long.
Yeah, the period's half as long. In other words, it's going twice as fast. So if I did that plot there, that's 2 pi there, and this is pi. Basically, it crams it in when time is equal to pi, at where I used to be at 2 pi. It's going to look like that. What does that do to the slope? If I'm looking at the slope of this versus the slope of this, steeper, shallower, same?
Steeper.
Yeah, it's steeper. I basically took this and I crammed it into half the space. If you imagine that this is sort of like an accordion there, if I cram it into half the space, it has to be steeper. Matter of fact, it's twice as steep. And how do I know twice? Got the number right there. If that had been a 3, it'd be 3 times. So what that happens, so when I do the slopes, it's still going to be a negative sign. And it's still 2t because it's still moving, sort of zipping around twice as fast, but that comes out wrong. Acceleration, well, every time you do a slope, this number just pops out front, so this becomes -4 cosine of 2t. So if I had x is equal to 4 cosine 17. What would the slope look like? The function for the slope?
Negative 21 sine 17.
Say it again?
Negative 21 sine 17.
Darn close.
Negative 28.
Thank you.
17.
Oh. Well. Started with.
All right. The next bit is if I am producing a wave. So imagine I've got a battle rope. For those who are not familiar with the term, or perhaps I'm using the wrong term, it's the exercise piece of equipment where you have a rope attached to the wall and basically you're doing this up and down. I got a couple of people who recognize it. All right, battle ropes? I got a couple of faint nods. Yes, I got more confident over there. All right. If I wanted to predict where if I want to sort of model the function of where a particular part of the rope is, do recognize that I'm sending a wave out in space, but also it's oscillating with time as well. So properly, if I really want to describe a wave, I really have two pieces to it. I have a time piece and I have a position piece. And so generically, I would write the wave as some amplitude, whatever it happens to be, cosine or sine, one of those two, times kx minus omega t. So that's an omega. And so here's position, time. This omega right here, that's the Greek letter, is the angular frequency. And this k right here is known as the wave number. Now, when I had this thing as respect to time here, I have this number right here, the omega. What is the period of this particular function here? In other words, how much time does it take before it starts to repeat itself? Yeah. What would be the period for this? And so we can generically say that the period is going to be 2 pi divided by omega.
How do we get that?
This basically tells you how fast it's moving. If you imagine a spinning clock, just where the arm can move. If it's just regular just a 1 there, then that's sort of consider that to be standard. 2, it's moving twice as fast, and so it takes half the time.
Okay.
If it takes, if it's 3, it's moving 3 times as fast, so it takes a third of the time. So normally it takes 2 pi to do it, and then you divide by whatever that number is.
We got that from cosine 17.
Yeah, it comes from the 7 right there.
Okay.
Whatever number is in front of the time, 2 pi divided by that tells you the period.
Okay.
In a similar manner, if I have y is equal to 3 cosine 4x, let's just start out with x. 3 cosine of x. At what point, what value of x does it start to repeat itself? Yeah, that 3 is just how tall it is. So we start out up here at 3 and negative 3, 2 pi. What is 2 pi then? What's the term that we use? It is not the period.
So wavelength.
Yes. Because we are now dealing with a distance here, and so that's at 2 pi, it starts to repeat itself in terms of distance. And so, doing similar thinking, the wavelength is going to be 2 pi divided by the wave number. Now, my recollection from math class is that they never really differentiate between period and wavelength. They give you a problem, it either has time or it has position in it, and they ask you find the wavelength or find the period, and you do whichever. It's 2 pi divided by whatever that number is. I don't recall them ever throwing something in where you actually have to do more thinking than, oh, it's 2 pi divided by that number. But there is a difference depending upon what the dependent variable is, or the independent variable is. All right, questions to here? All right, so if I have x is equal to, let's change that to say E is equal to some amplitude times the cosine of 5x minus 4t. Then, if I'm looking at the slope with respect to time, well, I care about the time piece. I don't worry about this one right here. I worry about the time. So I take the number in front here. Remember, just like you take this number here and you multiply it times that to get this. We take this -4 and we multiply it out front, so this would be -4 e sub 0. And then cosine goes to negative sine, so that becomes positive sine of 5x minus 14. If I did delta E over delta X, what would I get?
Might be -5.
Pardon?
-5, e sub 0, sine of 5x minus 14.
Yep. Because now I'm dealing with the x, I don't care about time, I care about the x piece. So I take the 5, because it's the one right in front of x, multiply it out front. Multiply it out front, there we go, better up here. So 5 times that, and then cosine becomes negative sine, given our chart over there. In calculus, it's called doing derivatives. Before calculus, it's called finding the slopes. All right, questions here? This is just hopefully enough to whet your appetite, just to build up the excitement for what we're about to do. I'm assuming that the people who are yawning are going to stop yawning at some point. Or maybe your brain will get so excited that it'll just tire you out faster. All right, here we go. All right, so we are dealing with an electric field that is oscillating back and forth. To properly describe this wave, we do need to have a position and time components to it, and this is the basic description of an electric field. Magnetic field, V sub naught cosine of kx minus omega t. And just so I keep track straight with my notes, let me make sure that I indeed started the other one with cosine. Oh, I started the other one with sine. It really should not matter. But in order to stay in sync with my notes, I'm going to start with sine. So we'll put this chart over here again, since we started with sine, which was down here. So this sine to cosine to negative sine to negative cosine, and then back to this. So what we're trying to do is trying to figure out the speed of a wave. So what is the definition of speed?
Distance traveled over time.
Yeah, that would have been really cool in unison. Distance over time, hopefully, is not a shock to you. So if I think about one complete cycle, the distance traveled is just the wavelength, and the time it takes to do it is just the period. We went through a similar derivation at the end of 151 for most of you. And the wavelength is 2 pi divided by k, and the period is 2 pi divided by omega. In 151, at this point, we do it slightly differently, since this becomes lambda times 1 over the period, which is lambda times the frequency. That's what we did in 151, so we're just wording it slightly differently. This becomes the 2 pi's cancel out, and what you're left with is 1 over k divided by 1 over omega, which is omega over k. So I'm going to write that off to the side because we're going to exploit that at some point. So V is equal to omega over k. Again, making sure I didn't get anything upside down because I'd hate to get through the whole derivation and then at some point go, ooh. Now, we're going to use 2 of Maxwell's equations here. We're going to do the sum of E dot delta L around a loop is equal to the negative change in magnetic flux over time. And we'll exploit B dot delta L around a loop is equal to mu naught I plus mu naught epsilon sub naught change in electric flux over time. This first one, Faraday-Lentz's law. And this is Ampere's law with Maxwell's correction. So Ampere's law stops at the plus sign right here, and this last bit was the part that we derived last time. This is the part that Maxwell brought into it, this being the displacement current. So current that is created based upon the movement of charges across a gap, in essence. So if I have an electric field, yeah, the room is really nice for this because I have a larger board, but we'll squeeze it in here. Hopefully everyone's vision is good enough. So if I have an electric field right here, it turns out that the magnetic field that's created, since this is a vector here, oops, I lost my vector. Sloppy notation, but I'm going with it anyway. As my electric field is going up and down like this on the board, my magnetic field actually is going to be perpendicular to that. They are perpendicular to each other. And so my magnetic field, this is my attempt at drawing in 3 dimensions, so do it however you need to. That's my attempt at a magnetic field coming out of the board. So notice how in sync the 2 graphs are. The fact that I drew 2 arrows in black and 3 in blue has no significance whatsoever. So basically the fields are like this to each other. All right, so let's start out with this one right here. What I'm going to do is I'm going to take a small little section here because I need, in order to be able to apply this, I need to have some sort of loop. I need some sort of, it could be 2-dimensional or 3-dimensional, but I'm going to take a 2-dimensional rectangle and basically put it on here. So I'm going to zoom in on this section right here. So my electric field looking very some small distance apart, so I'm just taking 2 moments of the electric field right next to each other. So my rectangle across this way is going to be, I want that to be delta x. And I'm taking that as my rectangle right there. I'm gonna blow that up here just because I want the room. So I have this, the electric field at some moment in time, and then the next moment in time, some tiny distance apart, probably a bit extreme there. And I'm creating my loop to look like that. This distance here is delta x, and this distance here is h. My magnetic field, when my electric field is going up, my magnetic field is coming out of the board, and so I'm going to represent my magnetic field as a vector coming out of the board. So it's I have my B field coming out of the board, and I have my electric field going up. You could do this for any part on here, but this is, why not here? This right here is my electric field. This one right here is gonna be my electric field plus some change. They're not the same, so there's some change, so it's just whatever this was plus a little bit more. I'm now gonna do my Gaussian loop there. I'm gonna start in this corner right here, and I'm going to go counterclockwise. So I'm gonna do my loop going this way. Just for the sake of notation, I'm gonna label this A, little b, C, and D. And so I start out with a sum of E dot D, not D, but delta L is equal to the negative change in the magnetic flux with respect to time. All right. So this E dot delta L, I'm basically doing a dot product between my electric field and my displacement on each of these lines here. So this would be, I'll have to break it up into 4 parts here. So this is E along path A dot delta L along path A plus E along path B dot delta L along path B plus, hopefully you can see a pattern here. We did something similar when we were finding the magnetic field inside a solenoid. And that's equal to the negative, well, magnetic flux is just B dot A. So this is the change in B dot A. Delta T. All right, so let's do it piece by piece. What is this equal to?
Change in flux or change in time.
I'm looking for just this piece right here.
It would be the electric field times the length of, wait, the L is length, right?
Yeah.
Length of A.
So for that first segment, what's the length? Nope, it's a distance, looking for a distance here.
Delta X.
I think somebody just said it.
Delta X.
Yeah, delta X. Yeah, it's just this from here to here, delta X. So what's the dot product between the electric field along this path and delta X?
0.
Why?
They're perpendicular.
Yes, delta L is going that way and delta X and E is that way. They're perpendicular to each other, so that's 0. Same reasoning, that's 0 also. So we have these two to worry about. What is along path B? First off, is it going to be 0? It's gonna be positive or negative.
I guess.
I'm getting a nod, yes, it's gonna be positive or negative, it's not zero. Okay, let's narrow that down.
Okay.
How do you do dot products?
Make up your axis.
Okay. In general, how do you do a dot product? What does dot product care about? Tell me something about dot products.
How much of one is is perpendicular to another?
Or
Parallel.
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 Cross is perpendicular. You know, cross has got perpendicular things. Dot's parallel. So how much is the electric field vector in the direction of our length?
All of it.
Yes, we're going from here to here, then up. In this segment here, our distance is up, our electric field is up. So when I do a dot product, what would the dot product be?
Just those put together, or twice as much, or
You're multiplying. So what do you mean put them together?
So it'd be just EL.
Pardon?
It would just be E times L.
What's E?
well, E plus delta E.
Yeah, okay, there's E. What's L?
Oh, so it's just squared.
No, what's L? I have it labeled, I put it on the board.
B.
B is just the name. H.
No.
E plus delta E times H. And then over here, what is this dot product?
E times H.
Missing one thing.
It'll be negative.
Negative. Yeah, because my electric field is going up, but our path here is going down at that point. We're trying to get back to the start. So this becomes negative EH is equal to, now I've got this change over here. My area is not changing because I said we're going to take this distance, this rectangular box right here, physical distances. So A basically comes out. My area vector is in the same direction as my magnetic field. And so this just becomes negative A times the change in the magnetic field over time.